I said in an earlier video that we would largely be looking at patterns, and this is going to reinforce that statement. We're going to integrate from 0 to pi over 4 the secant to the 6th of theta times the tangent to the 6th of theta d theta. The pattern that we notice we have here is that we have an even power for the secant function. When that's the case, I want to split up the secant function and break off essentially two factors. So I'm going to express this as secant to the 4th of theta and then secant squared of theta. As before, my reasons for doing this will become clear in a moment. We then have the integral from 0 to pi over 4 secant to the 4th of theta times the tangent to the 6th of theta times the secant squared of theta d theta. Our strategy in a case like this is to let du be the secant squared of theta d theta. And kind of working backwards, that would mean that u is equal to the tangent of theta. So where we see u to the, or tangent to the 6th of theta, we can think of that as u to the 6th of theta. As for the secant to the 4th of theta, we're going to use a Pythagorean identity that connects the secant and the tangent. We're actually going to think of this as the secant squared of theta squared. We end up with the integral from 0 to pi over 4 of the tangent squared of theta plus 1, the quantity squared, times the tangent to the 6th of theta times the secant squared of theta d theta. And we're now in a situation where, again, it looks like what we've done is made it worse. But we're about to make it a whole lot better. Our substitution is that u is equal to the tangent of theta. Therefore, the tangent squared of theta plus 1 quantity squared becomes u squared plus 1 the quantity squared. Tangent to the 6th of theta becomes u to the 6th. And secant squared of theta d theta becomes du. We are still integrating. We now have limits of integration that we need to deal with. So I'm going to set up a theta u table. Theta goes from 0 to pi over 4. Since u is equal to the tangent of theta, when theta is 0, u is 0. When theta is pi over 4, u is 1. So a quick recap. If I see a secant and a tangent together in an integral and an even power for the secant, I'm likely to break off two factors of secant, so secant squared theta d theta in this case. Let that be du, and that identifies u as the tangent of theta. Convert any remaining factors of the secant of theta using a Pythagorean identity, and this will work because if we started out with an even power for the secant and broke off an even power, we're left with an even power, and therefore we can use the Pythagorean identity. Now, having substituted, we can simplify the integrand by multiplying, foiling really the u squared plus 1 and then distributing the u to the 6th. We're going to end up with u to the 10th plus 2u to the 8th plus u to the 6th du from 0 to 1. And we can integrate that using the power rule. 1/11 times u to the 11th plus 2/9 u to the 9th plus 1/7 u to the 7th. This is evaluated from 0 to 1. The arithmetic turns out to be that the answer is 316 divided by 693. In our next example, we'll see another pattern with the tangent and the secant. We have the integral of the tangent to the 5th of x times the secant cubed of x dx. This time, what I'd like to note is that we have an odd power for the tangent function. If what we've done so far hasn't been tricky enough, here we are. We're going to break off 1 power of the tangent function and 1 power of the secant function. I know. Let's just see what we end up with. This is going to be the integral of the tangent to the 4th of x times the secant squared of x times the tangent of x times the secant of x dx. Looking here at the secant of x times the tangent of x dx, let's identify that to be our du. If that's the case, then u must be the secant of x. Based kind of on what you just saw in the previous exercise, I'd like for you to pause the video and see if you can finish this one. Tangent to the fourth of x can be expressed as tangent squared of x squared, and tangent squared of x can be replaced by secant squared of x minus 1. So we have the integral of secant squared of x minus 1, the quantity squared, times the secant squared of x times the secant of x tangent of x dx. Making a u substitution, this then becomes the integral of u squared minus 1, the quantity squared, times u squared du. And that was the whole point of recognizing that we had an odd power for a tangent and then identifying our du as secant of x tangent of x dx. Simplifying the integrand, we get the integral of u to the 6th minus 2u to the 4th plus u squared du. We're going to integrate using the power rule. I don't want to write down 2 more lines though. We know that u is equal to the secant of x. And so instead of writing 1/7 times u to the 7th, I'm going to write down 1/7 times the secant to the 7th of x. Likewise, minus 2/5 times the secant to the 5th of x plus 1/3 secant cubed of x plus c.